Welcome to day 22 of TryHackMe's 2024 Advent of Cyber. If you're new here, my name is Day and I'm a cybersecurity engineer at Amazon, and this channel is all about cybersecurity. I'm excited for the opportunity to be back on this year's Advent of Cyber, this time doing some Kubernetes digital forensics and incident response. Last year was Jenkins pipeline poisoning. If you want to check that out, it'll be linked in the description below or somewhere on the screen. And before we get into the video, be sure to like, subscribe, and share with any of your friends that you're working on this challenge with. Now, let's get into the video. All right. Task 28, day 22, Kubernetes DFIR. It's because I'm cubed, isn't it? That is actually very funny. All right, let's go and look at this story. Mayo malware laughed hard at what he had done. Another scheme hatched, another scheme won, but a thought passed the mayor. The thought then passed twice. The list soon to come, the towns naughty or nice. He paced and he paced, like the week of election. Until, that was it, a surprise mayor inspection. The list making wares, well, it only seemed fair. Would grant him temp access and account for the mayor. The list makers agreed, under certain conditions. He logged on that day to confirm his suspicions. The next day, they were, when the naughty list read. Mayor malware, line 1, he read it with dread. The conditions they gave, there's something they missed, as somehow and some way he accessed the list. Mayor malware then smiled, as he would find no blame. With this, he would find a new home for his name. It's quite the poem there, or the piece there. All right, so let's look at our learning objectives. And we have something here. We've seen mayor malware, so something we could keep an eye out for. Naughty and nice.nicetown.loc. Okay, naughty, nice, McSkitty, the glitch. All right, our learning objectives will be to learn about Kubernetes, what it is and why it is used, learn about DFIR, which is digital forensics and incident response, and the challenges that come with DFIR in an ephemeral environment. And then finally, learn how DFIR can be done in a Kubernetes environment using log analysis. Now, before moving forward, we can look at the questions here. Do we need to attack bugs today? No, we don't. Do we need to start a VM? We can do that right here. So let's start that. Is there a split screen available? Yes. Before we continue on, if you want to follow along while I also adjust between split screen and full screen, right here on the screen is the option at the bottom of the screen to allow you to go into the full screen mode so you can follow along just in case you ever have to move into a full screen mode, as I'll be doing in various parts of the video. Now back to the video. Is there a direct link available? No. All right, I think we're good to go. And while we wait for this to happen, let's go ahead and understand how Kubernetes works. Kubernetes Explained. Back in the day, it was very common for companies or organizations to use a monolithic architecture when building their applications. A monolithic architecture is an application built as a single unit, a single code base, and usually a single executable deployed as a single component. For many companies, this worked and still does to this day. However, for some companies, this style of architecture was causing problems, especially when it came to scaling. The problem with monolithic applications is that if one single part of the application needs scaling, the whole application has to be scaled with it. It would make far more sense for companies with applications that receive fluctuating levels of demand across their parts to break the application down component by component and run them as their own microservices. That way, if one microservice starts to receive an increase in demand, it can be scaled up rather than the entire application. The great microservice adoption. Microservices architecture was adopted by companies like Netflix, which is a perfect example of the hypothetical company discussed above. Their need to scale up services dedicated to streaming when a new title is released, while services dedicated to user registration, billing, and so on wouldn't need the same scaling level. This made a microservices architecture a no-brainer. As time went by, companies similar to Netflix hopped aboard the microservices express, and it became very widely adopted. Now, as for the hosting of these microservices, containers were chosen due to their lightweight nature. Only, as you may imagine, an application of this scale can require hundreds, even thousands of containers. Suddenly, a tool was needed to organize and manage these containers. Introducing Kubernetes. Well, you guessed it. That's exactly what Kubernetes was made for. Kubernetes is a container orchestration system. Imagine one of these microservices mentioned earlier is running in a container, and suddenly there's an increase in traffic, and this one container can no longer handle all requests. The solution to this problem is to have another container spun up for this microservice and balance the traffic between the two. Kubernetes takes care of this solution for you, orchestrating those containers when needed. In Kubernetes, containers run in pods, and these pods run on nodes, and a collection of nodes makes up a Kubernetes cluster. It is within a cluster that McSkitty and Co's investigation will occur today. If you're interested in learning more about Kubernetes, we have a range of rooms on the subject. A good place to start would be the Intro to Kubernetes room. Then, there's plenty more where that came from with the Kubernetes hardening module. Every cybersecurity cybersecurity professional has stumbled or will stumble upon DFIR at some point in their career. It's an acronym. In IT, we all love our acronyms, and that stands for Digital Forensics and Incident Response. These two investigative branches of cybersecurity come into play during a cybersecurity incident. A DFIR expert will likely be called to action as soon as an incident is ascertained and will be expected to perform actions that fall into one or both of the two disciplines. Will help McSkitty and Glitch become digital forensic analysts and retrace the malicious actor's steps. We'll especially focus on collecting evidence and artifacts to uncover the perpetrator and present our analysis to Wareville townspeople. And here we've got McSkitty and Glitch. Remember McSkitty from last year? Alright, let's talk about excruciatingly ephemeral. So, DFIR can be a lot of fun. It's easy to feel like a digital detective, analyzing the crime scene and connecting the dots to create a narrative string of events explaining what happened. What if the crime scene vanished into thin air moments after the crime was committed? That is a problem we face regularly when carrying out DFIR in a Kubernetes environment. This is because, as mentioned, Kubernetes workloads run in containers. It is very common that a container will have a very short lifespan, either spun up to run a job quickly or to handle increased load, and so on, before being spun back down. In fact, in these years, Cloud Native Security and Usage Reports, CISDIC found that 70% of containers live less than 5 minutes. So, what can we do about it? Well, not to worry. It just means we have to expand our digital detectives toolkit. The key to keeping track of the ongoings in your often ephemeral workloads within your Kubernetes environment is increasing visibility. There are a few ways we can do this. One way is by enabling Kubernetes audit login, a function that Kubernetes provides, allowing for requests to the API to be captured at various stages. For example, if a user makes a request to delete a pod, this request can be captured, and while the pod will be deleted and the logs contained within it lost, the request made to delete it will be persisted in the audit logs. What requests or events are captured can be defined with an audit policy. We can use these audit logs to answer questions which help us in a security/DFIR context, such as what happened, when did it happen, who initiated it, to what did it happen, where was it observed, from where was it initiated, and to where was it going. Now, of course, this just scratches the surface in terms of the level of visibility we can achieve in our Kubernetes environment. We can feed these audit logs as well as events from other security relevant sources into runtime security tools, which help transform these raw events into actionable data, which can then be visualized using yet more tools. A digital detective should definitely invest in an extra large toolkit. If you want to learn more on the subject, check out the Kubernetes runtime security room. All right, we've gone over the story, we've gone over the basics of Kubernetes containers, of Kubernetes audit login, of DFIR, and also DFIR for ephemeral environments. Let's get into the investigation. So, as mentioned before, some of our log sources would disappear as their sources, like pods, are ephemeral. Let's see this in action first. Let's go into our VM and open a terminal and start Kubernetes using the following command. Let's go ahead and do that. Open our terminal. All right, let's expand this. All right, let's go ahead and start our Kubernetes environment. And we're specifically using Minikube, which is kind of like a mini version of Kubernetes. And let's go ahead and start that. And this will take about 3 minutes for the cluster to configure itself and get started. All right, looks like our deployment is complete. So we can check if our cluster is up and running by running the kubectl get pods command -n where Ville. And what we're doing here is essentially using the kubectl utility, which is essentially a command line utility that helps us interact with, different aspects of a Kubernetes cluster, and then using get pods to list the pods within this cluster, and then specifying -n to specify the namespace of Wareville that we're dealing with here. So let's do that. And it looks like everything is running nice and good. All right, we're all set to continue on. So the next step here is if all of the pods are up and running based on their status, which we already have all is running, we're ready to go. This will take another 2 minutes. Since we know that the web application was compromised, let's connect to that pod and see if we can recover any logs. So we can do that by using a kubectl exec command. Now I'm going to walk you through the command here and what we're essentially doing using the exec utility of kubectl. So we're going to start by saying kubectl exec. An exec essentially allows us to execute a command inside of a container within a pod. So with the exec command, we're specifying -n again for the Wareville namespace, specifying the naughty or nice, and I misspelled that. That should be naughty right here, or nice pod. And then -it here is going to basically allow us to have an interactive shell. And then with -- /bin/bash essentially allows us to use the bash shell. Let's go ahead and run that. And now we're setting it as root within this naughty or nice pod. It's gonna clear our screen so we have more space down here. And then we're gonna go into our Apache access logs. So we'll do this by doing a cat var/log/Apache Apache2, and then our access log here. And this is pretty standard when you're dealing with applications. So let's go into that, and we have a bunch of logs in here. If we look, it looks like we are only getting logs from the 28th of October, and these logs appear to be a bunch of GET requests for our site. We have the user agent to be in this Ubuntu machine, more GET requests, more GET requests. Yeah, just a bunch of GET requests, and all within pretty short periods of time. Or probably someone browsing through the site, we see like, or probably enumerating the site, we see like API.php, index.js, right, tailwind.css, and a bunch of other stuff, right? We also see this right here, caught my eye right here. We see this shelly.php command who am I. This looks like some command injection right there, probably through the web interface. So that's definitely something we would want to dig into, but that didn't go unnoticed. So back here, we sadly only see logs from 20th of October when our attack occurred later on. Looking at the last log, however, we do see something interesting with the request being made to shelly.php. See, we mentioned that. So this tells us we're on the right track. Now, terminate your session to the pod using exit. So let's go ahead and exit. And we're going to keep in mind that we have that shelly.php, request there doing who am I, some sort of enumeration. And it kind of ties back into what we've seen over the course of this time period. A lot of GET requests over pretty short time spans, right? If you look at the time spans, like in this case right here, we see like, 12:32:37, 12:32:48, right? Really short time periods, right? Seconds or even milliseconds here. But let's go ahead and exit this. All right, let's clear our screen and back to our story here. So fortunately, McSkitty knew that the log source was ephemeral and decided to ensure that remote backups of the log source were made. So we'll navigate to our backup directory using cd/home/Ubuntu. And then we have a DFIR artifacts directory here. And we should be able to find the access logs stored in, let's see, pod _Apache2 _access log. And boom, we have some more logs in here. So we can review these logs to see what Mayor malware was up to on the site and answer the first 3 questions at the bottom of the task. Let's go ahead and do that before we continue on. So let's go ahead and answer the first 3 questions here. Scroll back down here. We have a lot of stuff to go through, but let's go through the first 3 questions. So what is the name of the web shell that was used by Mayor malware? Let's see. So I think it's pretty obvious here. The web shell is shelly.php, right? We already see that he's doing some who am I, some ls, some cat, right? And a bunch of other stuff, right? Which plus NC, right? They're just doing some enumeration here. So let's go ahead and submit shelly.php. All right, we got that right. What file did Mayor malware read from the pod? So it looks like they're catting db.php. So I think that's the file they're reading from the pod. So db.php. All right, and then what tool did Mayor malware search for that could be used to create a remote connection from the pod? We can find that right here, I believe. So which NC? So they're trying to find NC, which is like netcat, which is a utility for making remote connections or network connections from inside a Linux instance, which could be a container or a pod, whatever the case may be. So it looks like it's going to be netcat, which is sorting to NC here. All right, and we're good for the first 3 questions. Let's go back and continue on with where we were at in this investigation. All right, sadly, our investigation hits a bit of a brick wall here. Firstly, because the pod was configured using a port forward. We don't see the actual IP that was used to connect to the instance. Also, we still don't fully understand how the web shell found its way into the pod. Very good question. However, we rebooted the cluster and the web shell was present. Okay, meaning it must live within the actual image of the pod itself. That means we need to investigate the Docker image registry itself. To view the registry container ID, run the following command, docker ps. And this is basically like running let's go ahead and do this real quick. So Docker PS basically just lists all the running containers on the system. So the crazy thing about this, right, before we get back into the investigation, is that the attacker was actually able to compromise the image that the pod is being deployed from. So if the image is compromised from the, upwards registry, whatever it is, remote registry, that way, every single time this image is deployed at scale, it's always going to have that web shell, giving the attacker persistence for however long that discovery is not made that the image is actually malicious. So let's get back into our investigation and figure out how we're going to get rid of this. All right. So with our Docker PS command, we're kind of able to see the container ID, image, when it was created, and the status, the ports, and the command. Let's actually open this up in full screen so we can get a better view of this. It's kind of like mumbled up. All right, there we go. So we have the container ID, we see the registry, we see the command, it was created this long ago, and then see the status up about an hour, the ports, and then we have this other container. This is the Minikube one, right? We see the command, we see when it was created 7 months ago. It's been up for about 42 minutes. We see the ports, and the name is Minikube. So let's go back here and see what we're supposed to be doing next here. So it looks like our next step is going to be running a docker exec command, this container, and listing the contents of the var log directory to see if we have any more logs that would help us with our investigation. So let's go ahead and do this. So we're going to do a docker exec -it again. We've seen that command before. It's going to be for our interactive shell. In this case, we're not going to, leave it open. It will just close automatically. And then we're going to specify that container ID. Cool thing about Docker is you don't have to specify the entirety of the ID. So you could just specify a portion of it. And then we're just going to do ls-al to list the contents of that var log. Okay, looks like it's not auto-completing. Yeah, because it's inside the Docker container. So let's run that. And it looks like we have an empty directory here. Let's go back to our TryHackMe and see what we should do here. So within a wall, we don't have any registry logs, but luckily Docker itself would keep logs for us. Let's pull these logs using the following. So we can actually use Docker logs, right, to get those actual Docker logs. So again, we're going to use Docker logs to grab the details from this container ID. We're just going to specify the first few characters it has and pull that up. All right, looks like we have a bunch of details in our Docker logs. Let's kind of sift through this and see what we have here. So with a wider screen, we can kind of look at these a lot more better. Let's go up to the top and see if we can kind of, look through this massive heap of logs. Actually, I don't think we can, but there's a lot that we can see here. We can see the time, we have the info, and typically all of these details will be sent to like a SIM or some sort of like login or aggregation tool, right? But if not, you can see it from here, right? We see the messages, authorized requests, so we can see different messages for like requests, for responses. We can see the Go version, we can see the registry, right? This is for Nicetown. What else can we see? We can see the method, right? This is a head method right here. We can see the address, the remote address making this request to this particular container. We can see the URI. We can also see the user agent, where this is coming from. We can see that, for example, this looks like it came from a git commit, which is pretty interesting. And then we'll see there's a variable right here, wish list web. So we see a bunch of things, but there's a lot to go through here. We would have to like use some command line tool to kind of go through this. Let's go back into TryHackMe and move on with the next step. So we have something we can use now, and these logs have been pulled for us and are stored in the Ubuntu DFIR artifacts Docker registry -logs.log file. And we can start looking into the different connections that we've seen that were made to the registry by searching for the head HTTP request code and restricting it down to only the first term, which is the IP address. So it looks like we actually have these logs locally. So we're not going to have to like look through it from within these logs details. So let's go ahead and clear our screen. And then I think we're within the right directory. Okay, good. We're going to look into those registry logs. So we're going to look into those registry logs, and I'm going to break down the command we're going to be using in this case. So we're going to start with a cat, and the cat command is for us to just kind of look inside what is inside the Docker registry logs. And then we're piping that into a grep for head. And what this does is essentially just searches for the term head. And let me go back into our full screen here so we have more space to play with. Then we're piping those details that we get from, filtering down to just head as a keyword within those lines, using the COTS utility to split each line into fields, and then using -d for our delimiter, and then these two open quotes, and using space as a delimiter for that, and then tag F to select the very first field of what our outcome is. Let's run this and see what we get back. All right, so looks like the very first field, obviously for all the head requests are these IP addresses. And we see that we have a bunch of IP addresses here. We have 172.17.01 occurs multiple times here. And then we have 10.10, which is like a local IP address. And then we have, again, 172.17.01. So obviously we've seen that. And we can see that by far, most of the connections were from the 172.17.01 IP address. So our next step here is going to be to find all of the requests made by this IP address. So what we're going to do here is we're going to run that same cat command against the Docker registry logs. But this time we're just going to grab one of those IP addresses, which is going to be the 10.10.130.253. I'm going to clear this out right here. And I'm going to remove my video camera here so we're not blocking any log details. But here we see all of the requests that came from this 10.10.130 IP address. And we're getting somewhere with this, right? Let's go and look at the very first few requests and kind of see what is happening here. So we're seeing a bunch of GET requests. And then we get to this point where we have the GET requests being made to the manifests of the wish list image. We see that happen right here. It failed with the 404, but then it happened again and it succeeded with a 200 status code. Real quick, if you're not familiar with what a Kubernetes manifest is, it's essentially a configuration file that could be YAML or JSON, and it helps define the desired state of the resources that you want in your Kubernetes cluster, and essentially tells Kubernetes what you want to create or modify or manage or use within your environment, whether it's going to be pods, deployments, services, or other things that would determine your Kubernetes configuration. So that's what this attacker was actually able to get access to with that 200 status code. Let's get back into our investigation to see what happened next. Now, beyond that, we could also look into the user agent that is making the request. We see that all the user agents here are all Docker, right? All coming from Docker, Docker something, Docker something, Docker something. And what this actually signifies to us is that the requests were made through the Docker CLI to pull the image, as we've seen here. And if we continue down this whole request train, we see another GET request. We see another GET request, and this GET request retrieves blobs with a SHA-256 value, which is typically what is used to sometimes identify unique details about a specific object within a Kubernetes cluster, right? It could be like a pod or an image, right? It could be like an identifier for that image, right? And we see that this is all done using that Docker CLI over and over and over again. So what we know from this is that the Docker CLI was used to connect to the registry. And we see that requests were made from 10.10.130.253. And then finally, we can be pretty sure that whatever client was authenticating to this was authenticated and we're sure that we were able to pull the image because we have a 200 status code there, which means we're successful. And if this is happening, or if this has happened, that essentially means that whoever made these requests that were successful had access to some credentials. And if they had access to those credentials to pull an image, the same credentials might have allowed them to also push a new image, which was probably the compromised image that we discovered during our initial investigation. We can verify this by then narrowing down our search to look for any patch requests that were made, again from this IP address. Let's go back to our terminal. Let's just modify our command here by simply adding an additional keyword search for patch. Patch essentially is a request that modifies a resource. So we can do this and check for any patch requests. And here we see 2 patch requests. And these 2 patch requests are made to the wishlist web blobs uploads directory. And we get a 202 status code, which essentially means this was pretty successful. Essentially means it was in progress, but it was going to be successful. And we see this being done essentially from this same IP address. So this will essentially explain how the web shell made its way into the image. Since manual malware pulled the image, made malicious updates, and then pushed this compromised image back to the registry. Now we can use the information we have to answer questions 4 through 6 of the task. Let's go ahead and do that real quick. Back here, we're looking for the IP addresses that connected to the Docker registry that was unexpected. And we already know that IP address is the 10.10.130.253. All right. And at what time is the first connection made from this IP to the Docker registry. And we have to go back into our other logs here, which is this one. And let's go ahead and check that out. Actually, we can just do a head for that. Let's run that command again. So pipe that into head. And we should be able to get the first one, the first line here. And this should be the first connection that was made. So let's grab that in its entirety. This was on the 29th of October. Copy that. 10:06. Space that here. All right. And at what time is the updated malicious image pushed to the registry? We can get this from the patch command we saw previously. Let's go ahead and grab that. All right. So what time was the updated malicious image pushed to the registry? And this happened at this time right here. That was when it was done. Let's copy that. All right, let's get back into our investigation. Okay, so now that we know that Mayor malware had access to the credentials of the Docker registry, we need to learn how we could have gained access to them. We use these credentials in our Kubernetes cluster to read the image from the registry. So let's see what could have happened to disclose them. So we know that this attack happened via an authenticated Docker registry push, and we're sure about that because this was successful. Now it's time to turn to our Kubernetes environment and determine how this was possible. McSkitty was made aware that Mayor malware was giving user access to the naughty or nice Kubernetes environment, but was assured by the DevSecOps team that he wouldn't have sufficient permissions to view secrets and so on. The first thing we should do is to make sure that this is the case. So to do this, McSkitty decides to check what role was assigned to the Mayor, and she first checks the role bindings. Let's go ahead and do that. And the role bindings essentially is like what roles are bound to a user. And we're going to use the kubectl utility here again. So kubectl gets role bindings and specify the namespace of where we reveal. All right, looks like we have the job runner role and mayor user role. We can take a deeper look into these role bindings by using kubectl describe role binding. And first we're going to start by looking at the job runner role binding to see what essentially it is all about. Specify the namespace, where reveal. Let's look at that. It looks like name is job runner binding. Labels, no labels. Annotations, no annotations. Looks like it's a role. Its name is job runner. It's a service account. So real quick, essentially service accounts in Kubernetes are special accounts that are used by applications or processes or pods that are running within the cluster in order to interact with the Kubernetes API or other cluster resources. Unlike a regular user account that can represent a human, the service accounts are typically meant for applications. So in this case, this job runner is probably meant for some application that needs some jobs to be run. Now let's do the same thing for the mayor user binding account. Let's go ahead and do that. So the mayor user. So instead of job runner here, we're going to just replace that with mayor. Whoops. Mayor user. And it looks like we have same thing here, but this is a user, not a service account. And the name of this subject is Mayor malware. That definitely is concerning. So let's go ahead and look within that role. So I'm going to run this command again, but this time we're going to specify role instead of role binding to see the actual permissions that Mayor user has. So we see that the Mayor user has access to pods/exec, and this essentially allows them, like we've done before, to actually run commands in containers, and they're able to create, get, list for this resource. Next is role bindings. They're able to get, list, and describe role bindings. And then for roles that are back authorization, they're able to get, list, and describe that. For pods, they're able to get, list, and watch pods. So they mainly have enumeration permissions for these things right here. But for execution, they're able to create, get, and list. And this create permission could be really problematic, as we've seen in this case. So next, we can check the audit logs for Mayor malware's activity using this command right here. It's a pretty long one, so let's go through it. So we're essentially using a cat command to go through the audit log and then piping that into a grep and then specifying color always, which would basically highlight the matching text in color. And we're doing this across all of our greps. And then for this first one, we're specifically looking for a pattern that identifies the username of Mayor malware. Here we're also looking for where there's a resource value, and then we're also looking for where there's a verb value. So let's go ahead and run this. So let's kind of like look through what has happened here and see what this user has done. Especially what we've seen here in a nutshell is this Mayor malware first started by enumerating secrets. And when they enumerated the secrets, they didn't have sufficient permissions to do that. They got a bunch of errors for that. It failed for them. And then they went into enumerate roles, and they were able to identify various roles within the environment. And then they move on to enumerating roles, and afterwards enumerating role bindings, as we can see somewhere right here. In this case, they're actually able to find out about the role bindings, and they're actually enumerating the role bindings, specifically the access that they might have had through the job runner role, or even their own Mayor user role. And we see them further enumerating those role bindings. And then afterwards, enumerating for pods, as I can see right here, get, list, get, trying to identify the details within the pods. And we see here that when the pod is created, the pod is named as morality checker, which is pretty interesting. In addition to this, which we saw earlier on, we can see that Mayor malware is able to run commands within this pod, essentially using the exec utility. And as we've seen earlier on in the role discussion, the exec permission is usually not included in a non-admin role. And it's for this specific reason that Mosquito feels confident that the DevSecOps team had overly permissive role-based access control in place for this Kubernetes environment. And it was this exactly that allowed Mayor malware to run an exec command, as we've seen in the logs, and gain shell access into morality checker. So to confirm the suspicions a bit further, Mosquito, or us in this case, are going to run a command to retrieve audit logs captured from the job runner service account, which we saw earlier on. So we're going to use a similar command to what we used previously, but this time we're going to be looking for the username, system service account, specifically for the job runner service account, and then again specifying to look for the resource and the verb, and then we're going to search for that now. Let's see what's happening in here, starting from the top. So we can see that we have a list command right here, and they're listing for the secrets resource here. Kind of starting off the same way they did with the, with the other malicious account, then moving on to list another secret right here. And within this, we're actually able to see the details of the secret within the output right here. We see that the response object has those details. If we look within that, we see a bunch of details, stuff like data contains the secret data. Let's keep digging a little bit deeper. So again, another describing of the secrets. Again, specifically, I think the secrets that they pulled earlier on. And then next we have more secrets enumeration here. And it looks like this is like Docker configuration that they're pulling with regards to the secrets here. And then afterwards, more and more secrets enumeration here. So it looks like Mayor malware is now able to run that get command on the secrets that he wasn't able to run earlier on, which we saw previously. But most importantly, we can see that he's indeed been able to escalate his privileges and gain access to the pool cred secrets, which we saw there. So this is it. This is the final piece of the puzzle that revolved around the secret. Let's run a command to confirm the entirety of the attack path. So let's go ahead and look at what essentially was in this secret, and do that by running this command right here. And we already know this was in base 64, so we're going to be piping that into some base 64 code. Let's paste that. It's going to be a bit long, so let's go back to our long string here, run that, and we see those secrets indeed contained credentials, a username and a password, and possibly an authentication key. And so, shaking her head, Mosquito has confirmed, and we have confirmed that the Docker registry pull password is the same as the push password. And this means that after retrieving these credentials, Mayor malware would have been able to make the Docker registry push that we saw earlier and allowed him to deploy the malicious shell into the Kubernetes environment and maintain persistence. And it's for this reason that the push and pull credentials should always be different. And so with that being said, the investigation is all complete, and the conclusion is that Mayor malware most certainly belongs on the naughty list this year. We've solved the final piece of the puzzle, so let's go ahead and finish up the questions here. So back here, we're asked for what is the value stored in the pool cred secret. Let's go ahead and grab that. Actually, we can grab it from here, so we have it in all of its entirety. And that should do it. Awesome. Thank you so much for watching, and also to TryHackMe for setting this up and sponsoring this video. Be sure to check out tomorrow's challenge, or for some fun, try out this video on exploiting an indirect poison pipeline execution vulnerability with Jenkins that I did for last year's Advent of Cyber.